In this project, H-type vertical axis wind turbine is investigated. Nowadays, turbines are a reliable, clean energy source, which generates electricity using the induced rotation by wind flow. However, turbine wind farms face challenging issues such as low efficiency at lower diameters for horizontal axis turbines (HAWT), disruption of natural view of valleys, and low wind conditions. These three problems can be solved using vertical axis turbines VAWT, where diameter as large as 200 meter, commonly used in HAWTs, don't need. VAWTs are widely used offshore. Disruption of natural view is overcome and wind conditions are more predictable and reliable in offshore wind farms. Geometry of fluid domain is designed in Design Modeler and computational grid is generated using Ansys meshing. Mesh type is unstructured and element number is 1,546,624. Open the Ansys Fluent software. At first, you must read the mesh. We use the RNG-K epsilon model with the standard wall function as the turbulence model in this project. The RNG model was developed to renormalize the Navier-Stokes equations to account for the effects of smaller scales of motion. In the standard K-epsilon model, the eddy viscosity is determined from a single turbulence length scale, so the calculated turbulent diffusion is that which occurs only at a specified scale, whereas in reality all scales of motion will contribute to the turbulent diffusion. The RNG approach, which is a mathematical technique that can be used to drive a turbulence model similar to the K-epsilon, results in a modified form of the epsilon equation, which attempts to account for the different scales of motion through change to the production term. Although the technique for driving the RNG equations was quite revolutionary at the time, its use has been more low-key. Some workers claim it offers improved accuracy in rotating flows, although there are mixed results in this regard. It has shown improved results for modeling rotating cavities, but shown no improvements over the standard model for predicting vortex evaluation. Both these examples from individual experience. The standard wall functions are provided as a default option in Ansys Fluent. The standard wall functions work reasonably well for a broad range of wall-bounded flows. However, they tend to become less reliable when the flow situations depart from the ideal conditions that are assumed in their derivations. Among others, the constant shear and local equilibrium assumptions are the ones that must restrict the universality of the standard wall functions. Accordingly, when the near wall flows are subjected to severe pressure gradients, and when the flows are in strong non-equilibrium, the quality of the predictions is likely to be compromised. In In this dialog box, you can see the properties of the air material, which is the fluid selected for this simulation. You can change its properties by entering new values. The air fluid is set by default in the software, but you can define a new material in other simulation in this section or select a material from the Fluent database. In this project, we have two main zones, a stationary zone and rotational zone. Actually, the turbine rotates in z direction with an angular velocity equal to 14.17 radian per second, and the airflow in the domain is dominantly affected by turbine rotation. So we use the mesh motion to simulate the rotation. This is the dialog box for the rotational zone. Here, enable the mesh motion, then specify the rotation axis direction, and then enter the rotational velocity. In this box, you didn't need to set anything because this is the stationary zone. In the operating conditions dialog box, you must set the operating pressure and other operating conditions. Set the velocity inlet boundary type for the inlet boundary, and then in its dialog box, enter the velocity magnitude equal to 5.3 meter per second and turbulent intensity equal to 5% and turbulent viscosity ratio equal to 10. Select the pressure outlet for the outlet boundary, and then in its dialog box, enter the 5% for the backflow turbulent intensity and 10 for the backflow turbulence viscosity ratio. All valves must be stationary with no slip condition. Also set the symmetry boundary type for the symmetry. Now follow my cursor to learn how you can display the boundaries and see them. We use the simple scheme for pressure velocity coupling. Actually, this simple algorithm uses a relationship between velocity and pressure corrections to enforce mass conservations and to obtain the pressure field. For the discretization, we use the second order for the pressure and second order of wind for the momentum equation, and the first order of wind for the turbulent kinetic energy and turbulent dissipation rate. Now I want to show you how you can export and plot the moment coefficient in the graphic window during the solution. In this dialog box, at first you must select a report output type, moment coefficient or moment force. Then choose the walls. Also, you can enter the name for this report, and then you must specify the moment center and moment axis. Then if you enable the report file, the values of this moment coefficients will be right in the text file during the solution, and if you enable the report plot, you can have the plot of the moment coefficient in the graphic window during the solution. Also, if you enable the print to console, the moment coefficient values will be printed in the console box. All of these boxes must be disabled because if the remainder of this equation reach the absolute criteria values, the software thinks that the solution converges and stops solving, but we want the solution to continue as long as we want. To give the initial values to the center of all cells, select standard initialization. Then under the compute from, choose the boundary that you want to get the initial values from it. In this window, you can set the conditions under which your case and data will be saved during the solution. Enter the number you want in the box to store the case and data for each number. Also specify the path to save the files. In this section, enter the number of time steps and time step size, and then click on the calculate. The last thing I want to tell you in this section is how to save the case and data whenever you want. You can do it by clicking on the file, write case and data. Open the CFD Post software, and first you must read the results. See the next slides to learn how you can plot the contours, vectors, streamlines, and how you can save the picture of these plots. Also, how you can change the appearance of legend. According to rotation and free stream flow direction, there is a stagnation point in -y direction of the turbine, which represents maximum pressure zone 2. The combined effect of free stream flow and flow generated due to rotation is different on inner and outer blades. On internal blades, the pressure difference is less than the outer blades. This can be the result of the higher linear velocity of outer blades compared to linear blades. This table is an overview of the methods used in this simulation. In this table, you can see the models used, boundary conditions, discretizations methods, and initialization. To benefit from Master CFD services, including simulation, consultation, and training, contact our experts via info@master-cfd.com, www.master-cfd.com.